The Big Bang Theory, how did our universe begin? The Big Bang Theory. It's more than just a catchy sitcom title. It's the prevailing cosmological model for the universe. It describes the origin and evolution of everything we know. This theory isn't just a guess. It's built on a foundation of scientific observations and rigorous mathematical frameworks. It's the best explanation we have for how our universe came to be. According to the Big Bang Theory, our universe began approximately 13.8 billion years ago. It emerged from an extremely hot, dense state unlike anything we can imagine today. It's crucial to understand that the Big Bang wasn't an explosion in space. It was an expansion of space itself. Space, time, and matter all originated from this event. The very first moments after the Big Bang are shrouded in mystery. The extreme conditions make it difficult to fully understand what happened. The universe was incredibly small, perhaps smaller than an atom. It was filled with unimaginable energy, a sea of fundamental particles interacting at incredible speeds. As the universe expanded and cooled, fundamental forces began to separate. These forces govern all interactions in the universe. First, gravity separated, followed by the strong nuclear force, then the weak nuclear force and electromagnetism. Each separation marked a significant transition in the universe's evolution. In the first few minutes after the Big Bang, the universe cooled enough for the formation of the first atomic nuclei. This process is known as Big Bang nucleosynthesis. Primarily, hydrogen and helium nuclei were formed. These are the lightest and most abundant elements in the universe. The early universe was a hot, dense plasma of these nuclei and free electrons. This plasma was opaque to light, preventing photons from traveling freely. As the universe continued to expand and cool, something remarkable happened. Electrons combined with nuclei to form neutral atoms. This event is known as recombination, although the electrons and nuclei were combining for the first time. The formation of neutral atoms made the universe transparent to light. This transparency allowed photons to travel freely for the first time. These photons are still detectable today as the cosmic microwave background, or CMB. The CMB is the afterglow of recombination. It's a faint radiation that permeates the entire universe. The CMB is crucial evidence supporting the Big Bang Theory. It provides a snapshot of the universe as it was roughly 380,000 years after the Big Bang. After recombination, gravity began to play an increasingly important role. Tiny density variations in the early universe were amplified by gravity. These variations acted as seeds for the formation of larger structures. Regions with slightly higher density attracted more matter. Over time, these regions grew into the first stars, galaxies, and clusters of galaxies. The universe began to take on the structure we observe today. The Big Bang Theory is supported by a wealth of observational evidence. This evidence comes from various sources, including telescopes and particle accelerators. One key piece of evidence is the expansion of the universe. We observe this expansion through the redshift of distant galaxies. The redshift indicates that galaxies are moving away from us. The farther away a galaxy is, the faster it is receding. Another piece of evidence is the abundance of light elements, such as hydrogen and helium. The observed ratios of these elements align with the predictions of Big Bang nucleosynthesis. Finally, the cosmic microwave background provides strong support for the Big Bang Theory. Its properties match the predictions of a hot, dense early universe. Despite its success, the Big Bang Theory still leaves some questions unanswered. Scientists are actively researching these questions to refine our understanding of the universe. One major question is the nature of the initial singularity. What were the conditions at the very beginning of the universe? Another question concerns the origin of dark matter and dark energy. These mysterious substances make up the majority of the universe's mass and energy, but we don't yet know what they are. Scientists are also investigating the very early inflationary period. This period of rapid expansion may have occurred in the first fraction of a second after the Big Bang. The Big Bang Theory is the most comprehensive explanation we have for the origin and evolution of the universe. It explains a wide range of observations, from the expansion of the universe to the abundance of light elements. While some questions remain unanswered, the Big Bang Theory provides a solid foundation for our understanding of the cosmos. It continues to be refined and tested as we gather more data and develop new theories.
Planck Epoch. the smallest slice of time after the Big Bang. Welcome, fellow cosmic explorers, to a journey into the very beginning. We're diving into the Planck Epoch, the earliest moment in the universe we can even begin to contemplate. This incredibly brief period lasted a mere 10 to the power of -43 seconds after the Big Bang. That's one Planck time, an unimaginably small fraction of a second. The Planck epoch is shrouded in mystery. Our current understanding of physics simply breaks down at this scale. Space, time, and matter as we know them cease to behave predictably. Before this fleeting moment, the universe existed in a state beyond our comprehension. Imagine a density and temperature so extreme they defy description. The universe was a cauldron of unimaginable energy. All the forces that govern our reality were unified. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were one. They were indistinguishable aspects of a single unified superforce. The biggest hurdle in understanding the Planck epoch is gravity. We need to understand how it behaved at such a minuscule scale. Einstein's theory of general relativity describes gravity as the curvature of space-time. It works incredibly well for large objects like planets and galaxies. But at the Planck scale, space and time themselves are thought to be quantized. They exist in discrete units like tiny grains. This is where we need a theory of quantum gravity. It would reconcile general relativity with quantum mechanics. Quantum mechanics governs the behavior of matter at the subatomic level. It's a world of probabilities and uncertainty. Unfortunately, a complete and experimentally verified theory of quantum gravity remains elusive. It's one of the biggest challenges in modern physics. Some promising candidates include string theory and loop quantum gravity. These theories attempt to describe gravity in a way that is consistent with quantum mechanics. In the Planck epoch, the universe was likely dominated by quantum fluctuations. These were random, spontaneous variations in energy and spacetime. Think of them as tiny ripples in the fabric of reality. They popped in and out of existence constantly. These fluctuations could have played a crucial role in shaping the universe we see today. They may have seeded the initial density variations. These variations in density, however small, were amplified over time. They eventually led to the formation of galaxies, stars, and all the cosmic structures we observe. The Planck epoch is where the universe's initial conditions were set. It's the ultimate starting point for everything that followed. Understanding this epoch is crucial for answering some of the most fundamental questions in cosmology. What triggered the Big Bang itself? What was the initial size and shape of the universe? Was it a singularity, an infinitely small point? How did the universe evolve from this incredibly dense state to the vast, expanding cosmos we observe today? These are the questions that haunt cosmologists. Direct observation of the Planck epoch is impossible with current technology. The energy scales are far beyond anything we can recreate in a laboratory. So, scientists rely on theoretical models and indirect evidence. We use the power of mathematics and observation to piece together the puzzle. The cosmic microwave background radiation provides some insights. It's the afterglow of the Big Bang, a faint echo from the early universe. Future advancements in theoretical physics may offer more clues. New mathematical frameworks could unlock the secrets of quantum gravity. The detection of gravitational waves from the early universe could also help. These ripples in space-time could carry information from the Planck epoch. Our goal is to unlock the secrets of the Planck epoch. We want to understand the very beginning of everything. Ultimately, we seek a deeper understanding of the universe's origins. It's a quest to answer the biggest questions of existence. Cosmic inflation, how the universe expanded faster than light. Cosmic inflation is a mind-bending theory that revolutionized our understanding of the universe's earliest moments. It proposes a period of incredibly rapid expansion in the first fraction of a second after the Big Bang. This expansion wasn't just fast, it was faster than the speed of light. Inflation is crucial for explaining many of the observed features of the cosmos. It addresses fundamental issues that the standard Big Bang model simply can't account for. It's a cornerstone of modern cosmology. At the heart of inflation lies the concept of the inflaton field. This hypothetical field permeated the early universe, possessing an incredibly high energy density. This energy density acted as a repulsive force, driving the universe's exponential expansion. Think of it like a period of supercooling, where the universe was in an unstable, high-energy state. It was poised to explode outward, driven by the energy stored within the inflaton field. This explosion is what we call inflation. This explosive expansion lasted for an unimaginably short period, from about 10 to the power of minus 36 to 10 to the power of minus 32 seconds. Yet this tiny fraction of a second had profound consequences for the entire universe. It shaped the cosmos we observe today. The universe expanded by a factor of at least 10 to the power of 26 during this brief inflationary epoch. That's like taking something the size of an atom and instantly expanding it to the size of our solar system. This rapid expansion smoothed out the universe and set the stage for the formation of galaxies and stars. One of the biggest mysteries inflation solves is the flatness problem. Observations show that the universe is remarkably flat, meaning its geometry is very close to Euclidean. This is a puzzle because without inflation, the initial curvature of the universe would have needed to be incredibly fine-tuned. Any deviation from perfect flatness in the early universe would have been amplified over time. The universe would have either collapsed in on itself or expanded so rapidly that no structures could have formed. Inflation provides a natural explanation for this observed flatness. Inflation stretched the universe dramatically, smoothing out any initial curvature. Imagine blowing up a balloon. As it expands, its surface appears flatter and flatter. Similarly, inflation flattened the geometry of the universe. Another major puzzle addressed by inflation is the horizon problem. The cosmic microwave background, CMB, the afterglow of the Big Bang, is remarkably uniform in temperature across the entire sky. This uniformity is puzzling because in the standard Big Bang model, many regions of the CMB were never in causal contact. These regions were so far apart that light, the fastest thing in the universe, would not have had time to travel between them since the Big Bang. So, how could they have reached the same temperature? Inflation provides a compelling solution. Inflation suggests that these regions were once in very close proximity before the inflationary epoch. They were able to interact and reach thermal equilibrium. The subsequent rapid expansion then separated them, but they retained their uniform temperature. Inflation also provides a mechanism for generating the seeds of structure in the universe. Quantum fluctuations in the inflaton field, tiny random variations, were amplified during inflation. These amplified fluctuations became the initial density variations in the early universe. These density variations, though small, were crucial. Gravity acted upon them, pulling in more and more matter. Over billions of years, these variations grew into the galaxies, stars, and planets we see today. Without inflation, it's difficult to explain the origin of these initial density variations. Inflation provides a natural and elegant explanation for how the universe went from a nearly uniform state to the complex structure we observe. It's the reason we're here. While inflation is a remarkably successful theory, the exact details are still being researched. The inflaton field itself remains hypothetical. We haven't directly detected it. However, the theory has been remarkably successful in explaining key observations about the universe. Inflation provides a compelling framework for understanding the early evolution of the cosmos. It continues to be a major area of research in cosmology. Scientists are actively working to test and refine the theory. Ongoing research includes detailed observations of the cosmic microwave background. Scientists are searching for specific patterns in the CMB that would provide further evidence for inflation. These patterns are subtle, but potentially detectable. Another key area of research is the search for gravitational waves generated during inflation. These gravitational waves would be a direct signature of the rapid expansion. Detecting them would provide strong confirmation of the theory. The search for these gravitational waves is a challenging but potentially groundbreaking endeavor. It requires incredibly sensitive detectors and sophisticated data analysis techniques. If detected, they would open a new window into the very early universe. By studying the CMB and searching for gravitational waves, scientists hope to further test and refine the theory of inflation. They aim to understand the nature of the inflaton field and the precise details of the inflationary epoch. This research will help us unravel the mysteries of the universe's origins. The future of inflation research is bright. With new telescopes and detectors coming online, we are poised to learn even more about the universe's earliest moments. The quest to understand cosmic inflation is a quest to understand our place in the cosmos. Universe's first matter, the incredible story of quarks and gluons. The universe as we know it began with the Big Bang. But before there were atoms, stars, or even protons and neutrons, there was something else entirely, a primordial soup, a chaotic mix of the most fundamental particles. This soup consisted of quarks and gluons, the building blocks of matter as we know it. This exotic state of matter is known as the quark-gluon plasma, or QGP. It represents the universe's first matter, the very essence of existence. The quark-gluon plasma offers a glimpse into the raw ingredients of everything we see around us today. It's a window into the universe's infancy, a time of unimaginable heat and density. The quark-gluon plasma is a state of matter that is both extremely hot and incredibly dense. In this state, quarks are no longer confined within protons and neutrons. Instead, they roam freely, interacting with each other in a dynamic dance. These interactions occur through the strong force, one of the four fundamental forces of nature. Gluons are the mediators of this strong force, acting as messengers between the quarks. They are the glue that binds the universe together. The QGP existed for only a fleeting moment after the Big Bang. During this period, the universe was incredibly small and hot, a crucible of creation. Temperatures reached trillions of degrees Celsius, far exceeding anything we experience today. Understanding the quark-gluon plasma is crucial for understanding the evolution of the universe. It allows us to piece together the puzzle of how matter formed in the first moments after the Big Bang. Scientists aim to unravel the mysteries of the strong force through its study. A strong force is one of the four fundamental forces of nature, alongside gravity, electromagnetism, and the weak force. It binds quarks together within protons and neutrons, giving them their mass and stability. Without it, the universe would be a very different place. The QGP provides a unique laboratory to study the deconfined strong force. Physicists can probe the behavior of the strong force under extreme conditions, pushing the boundaries of our knowledge. This allows us to test our theories and refine our understanding of the fundamental laws of physics. Scientists recreate the quark-gluon plasma in particle accelerators like the Large Hadron Collider, or LHC, at CERN. This incredible feat of engineering allows us to simulate the conditions of the early universe. Heavy ions such as gold or lead nuclei are accelerated to near light speed. These ions are then collided head-on, generating conditions similar to those that existed moments after the Big Bang. The collisions create a tiny, short-lived QGP, a miniature version of the universe's first matter. This plasma expands and cools rapidly. Eventually, the QGP transitions back into ordinary matter, forming a shower of particles that detectors can measure. By studying these particles, we can learn about the properties of the QGP and the strong force that governs it. Analyzing the particles produced in these collisions provides invaluable insights into the properties of the QGP. Researchers study the flow patterns of particles, looking for clues about the plasma's behavior. They also study the production of specific particles, such as the J-psi meson. The J-psi meson is a bound state of a charm quark and a charm antiquark. Its production is suppressed in the QGP due to the deconfinement of quarks. This suppression serves as a key signature of the QGP's formation. Scientists also study the energy loss of particles traversing the plasma. This energy loss, known as jet quenching, provides information about the density and viscosity of the QGP. These observations help determine the temperature, density, and viscosity of the QGP. This provides a deeper understanding of its behavior and how it interacts with the particles that pass through it. By carefully analyzing these properties, we can paint a more complete picture of the QGP and its role in the early universe. The study of the quark-gluon plasma is a challenging but incredibly rewarding endeavor. It pushes the boundaries of our understanding of matter and the universe's origins. Scientists are gaining fundamental knowledge about the very fabric of reality. We are revealing the secrets of the universe's first matter, unlocking the mysteries of the strong force. This knowledge is essential for understanding its evolution into the cosmos we observe today. The QGP is a key piece of the puzzle. By continuing to explore this exotic state of matter, we can gain a deeper appreciation for the complexity and beauty of the universe. The journey to understand the QGP is a journey to understand ourselves and our place in the cosmos. Quark-gluon plasma, the universe's hottest particle soup. Imagine a state of matter so extreme, so energetic, that the very building blocks of reality are liberated. This is the quark-gluon plasma, or QGP. It's not your everyday solid, liquid, or gas. QGP is an extreme state of matter where quarks and gluons, normally confined within composite particles, are set free. This exotic plasma existed in the first few microseconds after the Big Bang. By recreating and studying QGP, we gain invaluable insights into the fundamental particles and forces that govern our universe. It's a journey back to the dawn of time, one collision at a time. To understand QGP, we must first delve into the standard model of particle physics. This model describes the fundamental particles and forces that make up all matter. Matter is composed of two primary types of fundamental particles, quarks and leptons. Leptons include electrons and neutrinos, while quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Quarks don't exist in isolation under normal conditions. They combine to form composite particles called hadrons, such as protons and neutrons. Protons and neutrons, in turn, make up the nuclei of atoms. These nuclei, surrounded by electrons, form the atoms that constitute all the matter we see around us. The force that binds quarks together within hadrons is the strong force. It's the most powerful of the 4 fundamental forces: dwarfing gravity, electromagnetism, and the weak force at short distances. The strong force is mediated by particles called gluons. Gluons act as the glue that holds quarks together, constantly exchanged between them. Under normal conditions, quarks are confined within hadrons. This phenomenon is known as quark confinement. However, under extreme conditions of high temperature and density, the strong force weakens. This weakening allows quarks to break free from their confinement. When the temperature reaches trillions of degrees Celsius, a phase transition occurs. Quarks and gluons are liberated from their hadronic prisons. This leads to the emergence of the quark-gluon plasma. Quarks and gluons exist as a deconfined, interacting soup. Since QGP existed only in the early universe, we can't simply observe it directly. Instead, we must recreate it in the laboratory. The primary method for creating QGP is colliding heavy ions, such as gold or lead nuclei, at near light speed. These collisions generate the extreme temperatures and densities required for deconfinement. 2 major facilities are at the forefront of QGP research: the Relativistic Heavy Ion Collider, or RHIC, at Brookhaven National Laboratory in the United States. The Large Hadron Collider, or LHC, at CERN in Switzerland also plays a crucial role. Both facilities accelerate heavy ions to incredible speeds and smash them together. These collisions generate temperatures exceeding trillions of degrees Celsius. That's far hotter than the core of the sun. The quark-gluon plasma is incredibly short-lived, existing for only a fleeting fraction of a second. This makes studying its properties a significant challenge. Scientists analyze the particles that emerge from these collisions. They look for specific signatures that indicate the formation and properties of QGP. One key signature is the suppression of certain particle production. This suppression occurs because quarks and gluons lose energy as they traverse the dense plasma. Another signature is the flow patterns of emitted particles. These patterns reveal information about the collective behavior of the plasma. The behavior of jets, collimated sprays of particles as they traverse the plasma, also provides valuable insights. The jets interact with the QGP, losing energy and modifying their structure. QGP exhibits fluid-like behavior, flowing with minimal resistance. It behaves like a nearly perfect fluid. This perfect fluid behavior is characterized by extremely low viscosity. Viscosity is a measure of a fluid's resistance to flow. Despite the deconfinement of quarks and gluons, the strong force still plays a crucial role in their interactions within the plasma. It dictates how these particles interact and influence the overall behavior of the QGP. Studying QGP helps us understand the evolution of the early universe. It provides a window into the conditions that existed shortly after the Big Bang. QGP research also sheds light on the formation of hadrons. It helps us understand how quarks and gluons eventually recombine to form protons, neutrons, and other composite particles. The study of quark-gluon plasma is a complex and ongoing endeavor. It requires cutting-edge technology and sophisticated theoretical models. Researchers hope to unlock further secrets about the universe. They aim to understand the fundamental nature of matter and the forces that govern it. QGP offers a glimpse into the universe's fiery past. It allows us to probe the conditions that existed at the very beginning of time. The birth of matter, how protons and neutrons formed in the early universe. Imagine the universe in its infancy, not as the vast cosmos we see today, but as a superheated, rapidly expanding soup of pure energy. This primordial state was the crucible where the very building blocks of matter were forged. From this chaotic beginning, a dramatic transformation occurred, the formation of protons and neutrons. These particles are the foundation of every atom, and therefore, everything we see around us. This process, known as Big Bang nucleosynthesis, is a cornerstone of modern cosmology. Understanding it unlocks profound insights into the universe's origins and evolution. In the immediate aftermath of the Big Bang, the universe was far too hot for stable particles to exist. Energy reigned supreme, constantly morphing and fluctuating. As the universe expanded, it began to cool. This cooling process was crucial, as it allowed energy density to decrease over time. This decrease in energy density paved the way for the formation of more stable structures. The universe was transitioning from a state of pure energy to one where matter could begin to take shape. Protons and neutrons aren't fundamental particles themselves. They are composed of even smaller particles called quarks and gluons. In the early universe, quarks and gluons existed in a free state, but as the universe cooled, these fundamental particles began to coalesce, drawn together by the strong nuclear force. This process, known as quark confinement, occurred within the first microsecond after the Big Bang. It was a pivotal moment in the universe's history. The exact mechanisms of quark confinement are still not fully understood by physicists. It remains one of the most challenging and fascinating areas of research. As the universe continued to cool, energy levels dropped further. This allowed quarks to bind together more stably, forming composite particles called hadrons. Among the most important hadrons to emerge were protons and neutrons. These particles would become the nuclei of the first atoms. A proton is composed of 2 up quarks and 1 down quark. These quarks are held together by the strong nuclear force, mediated by gluons. A neutron, on the other hand, consists of 1 up quark and 2 down quarks. The slight difference in quark composition gives neutrons a slightly higher mass than protons. The formation of protons and neutrons was a crucial step towards the formation of atomic nuclei. Without them, the universe would be a very different place. In the early universe, protons and neutrons could readily convert into each other. This conversion was driven by interactions with other particles, such as electrons and neutrinos. Initially, there was a state of equilibrium between protons and neutrons. The rate of conversion from protons to neutrons was roughly equal to the rate of conversion from neutrons to protons. However, as the universe cooled, this equilibrium began to shift. The formation of protons became slightly favored over the formation of neutrons. This shift was due to the fact that neutrons are slightly heavier than protons. Therefore, more energy was required to create a neutron than a proton. About 1 second after the Big Bang, the universe had cooled to approximately 1 billion degrees Kelvin. At this temperature, the conversion between protons and neutrons began to slow down significantly. The ratio of protons to neutrons stabilized at roughly 7 protons for every neutron. This ratio was critical for the subsequent formation of light elements. If the ratio had been significantly different, the composition of the universe would be drastically altered. The formation of stars and galaxies might not have been possible. This precise ratio highlights the delicate balance of physical laws that govern the universe. Even slight variations could have profound consequences. As the universe continued to cool, protons and neutrons began to fuse together. This process, known as Big Bang nucleosynthesis, resulted in the formation of light atomic nuclei. The primary elements formed during this period were deuterium, helium-3, helium-4, and trace amounts of lithium. These elements are the building blocks of the first stars. The most abundant element formed was hydrogen, which is simply a single proton. Approximately 75% of the universe's mass was in the form of hydrogen. The second most abundant element was helium-4, making up about 25% of the universe's mass. The remaining elements were present in only trace amounts. The formation of protons and neutrons, along with Big Bang nucleosynthesis, were pivotal events in the history of the universe. These processes laid the foundation for everything that followed. These early events set the stage for the formation of atoms, stars, and galaxies. Without them, the universe as we know it would not exist. The abundance of light elements observed in the universe today provides strong evidence for the Big Bang theory. It is one of the most compelling pieces of evidence supporting our current understanding of the universe's origins. Studying the formation of protons and neutrons allows us to probe the universe's earliest moments. It provides a window into the extreme conditions that existed shortly after the Big Bang. Understanding these processes is crucial for unraveling the mysteries of the universe. It helps us to answer fundamental questions about our place in the cosmos. Big Bang nucleosynthesis: how the universe made its first atoms. Have you ever wondered where the atoms that make up everything around us came from? The answer lies in the very early universe, during a period known as Big Bang nucleosynthesis, or BBN. BBN refers to the formation of the first atomic nuclei in the minutes following the Big Bang. It's a crucial cornerstone of the Big Bang theory itself. This process explains the observed abundance of light elements like hydrogen and helium in the cosmos. In fact, BBN provides some of the strongest evidence we have for the validity of the Big Bang theory. Imagine the universe just moments after its birth. It was an incredibly hot and dense soup of fundamental particles. This primordial soup contained quarks, leptons, and photons, all interacting at unimaginable energies. As the universe expanded and cooled, these particles began to interact in new ways. Quarks, for example, combined to form protons and neutrons, the building blocks of atomic nuclei. However, in the earliest moments, conditions were simply too energetic for these nuclei to remain stable. The era of Big Bang nucleosynthesis began approximately 1 second to 3 minutes after the Big Bang. By this point, the temperature had dropped to a point where nuclear fusion could occur. Protons and neutrons began to collide and fuse together, initiating the creation of the nuclei of the lightest elements. This was the universe's first act of alchemy. It was a period of rapid and intense nuclear activity, laying the foundation for the chemical composition of the universe we see today. The primary reaction in BBN was the fusion of a proton and a neutron to form deuterium, a heavy isotope of hydrogen. Deuterium acted as a crucial stepping stone for the creation of heavier elements. Further fusion reactions led to the formation of helium-3, another light isotope of helium. But the most abundant element produced during BBN was helium-4. In addition to hydrogen and helium isotopes, trace amounts of lithium-7 were also synthesized during this period. These light elements are the legacy of BBN. The rapid expansion of the universe played a crucial role in limiting the extent of BBN. As the universe expanded, its density and temperature decreased rapidly. This expansion eventually halted further fusion reactions. There was simply not enough time or energy to create heavier elements in significant quantities. Another key limitation was the lack of stable nuclei with a mass of 5 or 8. This gap in nuclear stability prevented the formation of heavier elements like carbon and oxygen during BBN. These heavier elements, essential for life as we know it, would have to wait for the formation of stars and the process of stellar nucleosynthesis. Despite its limitations, Big Bang nucleosynthesis is a remarkable success story. It accurately predicts the observed abundance of light elements in the universe. BBN predicts specific ratios of hydrogen, helium-4, helium-3, and lithium-7. These predictions align remarkably well with astronomical measurements. This agreement between theory and observation provides strong support for the Big Bang model. It confirms our understanding of the conditions and processes that occurred in the early universe. The success of BBN is a testament to the power of physics to explain the cosmos. It's a cornerstone of modern cosmology. Big Bang nucleosynthesis was the cosmic forge where the first atomic nuclei were created. It laid the foundation for the formation of stars, galaxies, and ultimately everything we see around us. Without BBN, the universe would be a very different place. It was essential for the formation of the complex structures we observe today. The story of BBN is a testament to the power of physics to unravel the mysteries of the universe. It's a remarkable story of the universe's beginning. It highlights how fundamental processes in the early universe shaped the cosmos we inhabit today. The elements forged in those first few minutes continue to influence the universe's evolution. So, the next time you look up at the stars, remember the Big Bang nucleosynthesis. Remember the cosmic forge that created the building blocks of our universe. Before we dive deeper into the reactions, let's paint a clearer picture of the early universe. Imagine a time when the universe was far smaller, hotter, and denser than anything we can comprehend today. This wasn't a void, but a seething soup of fundamental particles. Quarks, leptons like electrons and neutrinos, and photons were all crammed together in a state of extreme energy. The temperature was so high that atoms couldn't even exist. Any attempt to form a nucleus would be immediately disrupted by the intense heat and collisions. As the universe expanded, it began to cool. This cooling was crucial, as it allowed particles to combine and form more complex structures. Quarks, for instance, started to bind together to form protons and neutrons. These are the building blocks of atomic nuclei, and they would play a central role in BBN. The ratio of neutrons to protons in the early universe was a critical factor in determining the outcome of BBN. Initially, neutrons and protons were in thermal equilibrium, meaning they could readily convert into each other. However, as the universe cooled, this equilibrium began to break down. Neutrons are slightly heavier than protons, and it became energetically more favorable for protons to exist. This led to a gradual decrease in the neutron-to-proton ratio. By the time BBN began, there were significantly fewer neutrons than protons. This imbalance had a profound impact on the types and amounts of elements that could be formed. It's a delicate balance that shaped the universe's composition. The formation of deuterium was the first major hurdle in BBN. Deuterium, a heavy isotope of hydrogen, consists of one proton and one neutron. However, deuterium is relatively fragile. It can be easily broken apart by high-energy photons. In the early universe, there were plenty of these photons around. This created a deuterium bottleneck, preventing the formation of heavier elements until the temperature dropped sufficiently. Only when the universe cooled enough for deuterium to survive could BBN truly get underway. This delay had significant consequences for the final abundance of elements. Once deuterium formed, it quickly reacted with protons and neutrons to produce heavier elements, primarily helium-4. Helium-4 is an exceptionally stable nucleus, consisting of 2 protons and 2 neutrons. A vast majority of neutrons present in the early universe ended up bound in helium-4 nuclei. This explains why helium-4 is the second most abundant element in the universe, after hydrogen. The amount of helium-4 produced during BBN is remarkably sensitive to the expansion rate of the universe. This makes it a powerful tool for probing the conditions of the early cosmos. While BBN's predictions for hydrogen and helium are in excellent agreement with observations, there's a persistent discrepancy when it comes to lithium-7. Observations suggest that there is less lithium-7 in the universe than predicted by BBN. This is known as the lithium problem, and it remains an active area of research. Scientists are exploring various possible explanations, including uncertainties in nuclear reaction rates, the presence of exotic particles, or even modifications to the standard cosmological model. The lithium problem highlights the fact that our understanding of the early universe is not yet complete. It's a reminder that there are still mysteries to be solved. BBN produced the raw materials for the first stars. These stars, born from the primordial soup of hydrogen and helium, were vastly different from the stars we see today. They were much more massive and short-lived, and they played a crucial role in enriching the universe with heavier elements through stellar nucleosynthesis. This is the process by which stars fuse lighter elements into heavier ones in their cores. The heavier elements created in these first stars were then dispersed into the universe through supernova explosions. These elements became the building blocks for future generations of stars and planets. In essence, BBN laid the foundation for the entire cycle of stellar evolution and the creation of the elements that make up our world. Big Bang nucleosynthesis is not just a confirmation of the Big Bang theory, it's also a powerful tool for probing new physics beyond the standard model. The abundance of light elements is sensitive to various cosmological parameters, such as the baryon density and the number of neutrino species. By comparing BBN predictions with observations, scientists can place constraints on these parameters and search for deviations from the standard model. For example, BBN can be used to constrain the properties of dark matter and dark energy. It can also be used to test theories of modified gravity in extra dimensions. In this way, BBN serves as a window into the very early universe and the fundamental laws of nature. Big Bang nucleosynthesis is a remarkable achievement of modern cosmology. It provides a compelling explanation for the origin of the light elements and offers strong support for the Big Bang theory. It's a testament to the power of scientific inquiry and the ability of humans to understand the universe around us. The story of BBN is a story of discovery, innovation, and the relentless pursuit of knowledge. The elements forged in the first few minutes of the universe continue to shape the cosmos today. They are the building blocks of stars, planets, and ultimately life itself. So, the next time you look at a periodic table, remember the Big Bang nucleosynthesis. Remember the cosmic forge that created the elements that make up our world. The dark universe, when light was trapped in cosmic shadows. Imagine a time when the universe was shrouded in darkness, a cosmic mystery veiled from our sight. This is the era of the dark universe, a period dominated by the absence of light. It's a crucial chapter in cosmic history, holding the key to understanding the universe's evolution. In the immediate aftermath of the Big Bang, the universe was an incredibly hot and dense plasma. As the universe expanded and cooled, a pivotal event occurred: recombination. Protons and electrons, previously existing freely, combined to form neutral hydrogen atoms. This transformation took place approximately 380,000 years after the Big Bang. It marked a significant shift in the universe's composition and its interaction with light. Neutral hydrogen, now abundant, played a crucial role in trapping light. It efficiently absorbed photons, particularly those with a specific wavelength, corresponding to the Lyman alpha transition. This wavelength is key to understanding how light interacted with the early universe. The scattering and absorption of light by neutral hydrogen rendered the universe opaque. For hundreds of millions of years, the cosmos remained shrouded in darkness, a period we call the Dark Ages. Despite the darkness, the universe continued to evolve. Expansion and cooling persisted, setting the stage for the next major development. Gravity, the architect of cosmic structures, began to exert its influence on subtle density fluctuations. These fluctuations, tiny variations in the distribution of matter, became the seeds of future structures. Gravity amplified these differences, leading to the formation of regions with higher density. These denser regions eventually collapsed under their own gravity. This collapse marked the birth of the first stars and galaxies, the first beacons of light in the dark universe. The first stars, known as Population 3 stars, were unlike anything we see today. They were massive, hot, and short-lived, emitting intense ultraviolet radiation. This radiation initiated a process called reionization. The ultraviolet photons from these early stars began to ionize the surrounding neutral hydrogen. This process created bubbles of ionized gas around the first stars and galaxies. These bubbles expanded and eventually merged, clearing the fog of neutral hydrogen. Reionization marked the end of the Dark Ages, ushering in the era of observable galaxies. The universe transitioned from opaque to transparent, allowing light to travel freely across vast cosmic distances. Studying the Dark Ages presents significant challenges. The era is characterized by the absence of light, making direct observation difficult. However, scientists are employing innovative techniques to peer into this cosmic past. Observations of the cosmic microwave background, CMB, provide a snapshot of the universe just before recombination. The CMB is the afterglow of the Big Bang, a faint radiation that permeates the cosmos. It offers valuable clues about the conditions that existed at the end of the early universe. Powerful telescopes are being used to search for faint signals from the Dark Ages. One promising avenue of research involves the 21-centimeter signal. This signal is emitted by neutral hydrogen and can potentially reveal its distribution throughout the Dark Ages. By studying the 21-centimeter signal, scientists hope to understand the formation of the first stars and galaxies. This would provide invaluable insights into the processes that shaped the early universe. The study of the dark universe is a rewarding endeavor. It offers a glimpse into the very beginnings of the cosmos. By understanding this era, we can unravel the processes that shaped the universe we see today. The Dark Ages hold the key to understanding the formation of the first stars and galaxies. It reveals how the universe transitioned from a simple, homogeneous state to the complex, structured cosmos we inhabit. Ultimately, the study of the dark universe leads to a deeper understanding of our place in the universe. It reminds us that we are part of a vast and evolving cosmic story. Cosmic Dawn, the epic moment light broke free from matter. The cosmic dawn marks a pivotal epoch in the early universe, a transformative period when darkness gave way to light. It represents the transition from a dark, opaque state to a luminous one, forever altering the cosmos. This era occurred roughly 200 to 400 million years after the Big Bang. During the cosmic dawn, the first stars, galaxies, and quasars were born, igniting the universe with their radiant energy. These nascent structures fundamentally shaped the universe we observe today, influencing its evolution and composition. Understanding the cosmic dawn is crucial to unraveling the mysteries of our cosmic origins. Prior to the cosmic dawn, the universe existed in a vastly different state. It was a dense, hot soup of ionized plasma, a chaotic mixture of particles. This era, preceding the emergence of light, is aptly named the Dark Ages. The Dark Ages were dominated by neutral hydrogen atoms. These atoms, while simple in structure, played a crucial role in shaping the early universe. Neutral hydrogen atoms efficiently absorb photons, effectively trapping light. This absorption prevented light from traveling freely through the cosmos. The universe remained shrouded in darkness, awaiting the spark that would ignite the cosmic dawn. The Dark Ages set the stage for the dramatic events that would soon unfold. The gradual cooling and expansion of the universe played a critical role in ending the Dark Ages. As the universe expanded, its temperature decreased, allowing for new interactions. Electrons and protons combined to form neutral hydrogen atoms, a key step in the process. Gravity, the universal force of attraction, also played a crucial role. It acted on tiny density fluctuations that existed in the early universe. Regions with higher densities attracted more matter, gradually increasing their gravitational pull. This process led to the collapse and formation of the first stars and galaxies. These nascent structures would ultimately drive the cosmic dawn, illuminating the universe. The interplay of cooling and gravity was essential for the emergence of light. The nascent celestial objects, the first stars, drove the cosmic dawn. These stellar pioneers were unlike anything we see today. The first stars were likely massive and short-lived, burning through their fuel at an incredible rate. They emitted intense ultraviolet radiation, a powerful form of energy. This radiation interacted with the surrounding neutral hydrogen. The ultraviolet radiation ionized the surrounding neutral hydrogen, stripping away its electrons. This process effectively reionized the universe, reversing the conditions of the Dark Ages. The first stars acted as cosmic lighthouses, piercing the darkness and paving the way for the cosmic dawn. Their impact on the early universe was profound and transformative. Reionization was a pivotal process that cleared the cosmic fog. It created bubbles of ionized gas around the first stars and galaxies. These bubbles gradually expanded and merged, growing larger over time.
As the bubbles expanded, they cleared the fog of neutral hydrogen. This allowed light to propagate freely through the universe. Reionization marked a significant turning point in cosmic history. The universe transitioned from an opaque state to a transparent one. Light could now travel vast distances, revealing the structures that were forming. Reionization was a crucial step in shaping the universe we observe today. The formation of the first galaxies further contributed to reionization. These galaxies contained vast numbers of stars, each emitting its own light. They provided a continuous source of ionizing radiation, sustaining the reionization process. Quasars, powered by supermassive black holes, were also incredibly luminous. These cosmic beacons emitted powerful jets of energy. These jets further contributed to ionization, clearing away the remaining neutral hydrogen. Galaxies and quasars amplified the light of the cosmic dawn. They played a crucial role in shaping the large-scale structure of the universe. Their combined energy transformed the cosmos, paving the way for the formation of more complex structures. Observing the cosmic dawn presents a major challenge for astronomers. The light from these early objects is incredibly faint. It has traveled billions of light years to reach us, dimming along the way. Furthermore, the light has been stretched by the expansion of the universe. This stretching shifts the light into the infrared spectrum. This makes it difficult to observe with traditional telescopes. However, advancements in telescopes are providing unprecedented glimpses into this era. Telescopes like the James Webb Space Telescope are revolutionizing our understanding of the cosmic dawn. These advancements represent a triumph of human ingenuity and scientific curiosity. The James Webb Space Telescope, or JWST, is a revolutionary tool for studying the cosmic dawn. Its infrared capabilities allow it to peer through cosmic dust. This dust obscures the view of many other telescopes. JWST can observe the light from the first stars and galaxies. It provides valuable insights into their formation and evolution. It helps us understand their role in shaping the universe. JWST is providing unprecedented data about the early universe. It is helping us unravel the mysteries of the cosmic dawn. It is a testament to our ability to explore the cosmos and understand our place within it. Studying the cosmic dawn is crucial for understanding the origins of everything we see today. It allows us to learn about the processes that led to the formation of the elements. It helps us understand the distribution of matter in the universe. It also helps us understand the evolution of the universe from its earliest moments to the present day. The cosmic dawn represents a crucial turning point in cosmic history. It is a period of rapid change and transformation. By studying the cosmic dawn, we can gain a deeper understanding of our place in the universe. We can learn about the processes that shaped our cosmic environment. We can appreciate the incredible journey that has led to our existence. The cosmic dawn is a window into the past, offering profound insights into the present and future of the cosmos. Galaxy evolution, the secrets behind spiral and elliptical galaxies. Galaxies are the fundamental building blocks of the universe, vast islands of stars, gas, and dust bound together by gravity. Among the diverse galaxy types, spiral and elliptical galaxies stand out as two of the most common and distinctly different. Understanding the differences between these galactic forms and how they evolve is crucial to unraveling the universe's history. Spiral galaxies are characterized by their flattened, rotating disk adorned with graceful spiral arms. At the heart of most spiral galaxies lies a central bulge, a dense concentration of stars. Many spiral galaxies also harbor a supermassive black hole at their core, exerting a powerful gravitational influence. One of the defining features of spiral galaxies is their active star formation, primarily occurring within the spiral arms. These arms are rich in gas and dust, the raw materials needed to birth new stars. The presence of young, hot, blue stars gives spiral galaxies their vibrant appearance. Spiral galaxies are typically found in less dense regions of the universe, away from the crowded environments of galaxy clusters. This relatively isolated environment allows them to maintain their delicate spiral structure. It also allows them to continue drawing in fresh gas and dust, fueling ongoing star formation. The evolution of spiral galaxies is largely driven by internal processes, particularly the rate of star formation. As stars form,
They consume the galaxy's supply of gas. Our own Milky Way galaxy serves as a prime example of a spiral galaxy, steadily evolving over billions of years.
Elliptical galaxies present a stark contrast to their spiral counterparts. They exhibit a smooth, ellipsoidal shape, lacking the distinct spiral arms that define spiral galaxies. Elliptical galaxies are dominated by older, redder stars, indicating a different history of star formation. Unlike spiral galaxies, elliptical galaxies have largely ceased forming new stars. They contain very little gas and dust, the essential ingredients for star birth. The raw materials needed for new stars have either been depleted or expelled from the galaxy. Elliptical galaxies are often found in dense environments, such as the centers of galaxy clusters. In these crowded regions, gravitational interactions with other galaxies are common. These interactions play a significant role in shaping the evolution of elliptical galaxies. The prevailing theory suggests that elliptical galaxies form through the mergers of spiral galaxies. When two or more spiral galaxies collide, their gravitational forces disrupt their structures. The collision strips away much of the gas and dust, triggering a burst of star formation. After the merger, the resulting galaxy settles into a more spherical or ellipsoidal shape. The older stars, which were already present in the merging galaxies, come to dominate the overall appearance. The once distinct spiral arms are lost in the chaotic mixing of stars. Galactic cannibalism, where a larger galaxy consumes a smaller one, is a key driver of elliptical galaxy formation and growth. Over time, a large elliptical galaxy can grow even larger by swallowing up smaller galaxies that venture too close. This process further contributes to the galaxy's smooth, featureless appearance. The dense environments of galaxy clusters exert a powerful influence on galaxy evolution. One important process is ram pressure stripping, where the hot gas in the cluster sweeps away the gas and dust from galaxies moving through it. This stripping hinders star formation and contributes to the transformation of spiral galaxies into elliptical galaxies. Tidal forces, the gravitational forces exerted by one galaxy on another, can also distort and reshape galaxies. These forces can stretch and pull galaxies, creating tidal tails and other unusual structures. Tidal forces play a significant role in influencing the evolution of galaxies in interacting systems. Galaxy evolution is a complex interplay of internal processes, environmental factors, and gravitational interactions. Internal processes, such as star formation, drive the evolution of individual galaxies. Environmental factors, such as the density of the surrounding region, can significantly impact a galaxy's fate. Gravitational interactions, such as mergers and tidal forces, can dramatically reshape galaxies and trigger bursts of star formation. Spiral galaxies are characterized by ongoing star formation and a disk-like structure, while elliptical galaxies are dominated by older stars and have an ellipsoidal shape, often resulting from mergers. By studying galaxies, we can gain a deeper understanding of the universe's history and its ongoing transformation. The secrets held within these vast cosmic structures continue to reveal the intricate processes that have shaped the universe we observe today. From stardust to gold, the violent origins of heavy elements. The universe, in its vastness and complexity, is fundamentally composed of elements. These elements, from the lightest to the heaviest, dictate the properties of matter and the very fabric of reality. But where did these elements come from? Hydrogen and helium, the simplest and most abundant elements, originated in the immediate aftermath of the Big Bang. However, the heavier elements, the building blocks of planets, life, and technology, have a more dramatic and violent origin story. The creation of these heavy elements is a tale of cosmic evolution, driven by the relentless force of gravity and the transformative power of nuclear fusion. It's a story written in the hearts of stars and the cataclysmic explosions that mark their demise. Stars are the cosmic furnaces where lighter elements are forged into heavier ones through a process called nucleosynthesis. Within their cores, immense pressure and temperature create the conditions necessary for nuclear reactions to occur. Lighter elements, like hydrogen, are fused together to form helium, releasing tremendous amounts of energy in the process. This is the same process that powers our sun, and provides light and warmth to our planet. As a star ages, it begins to fuse helium into carbon, and then carbon into progressively heavier elements like oxygen, neon, silicon, and sulfur. This process continues, layer by layer, like the rings of a cosmic onion. A process continues up to iron. Iron is a pivotal element in the life cycle of a star. It represents a turning point in the process of stellar nucleosynthesis. Iron is the most stable of all elements. Fusing iron requires more energy than it releases. This marks the beginning of a star's inevitable demise. Massive stars, those many times larger than our Sun, meet a spectacular end in the form of supernovae. When a massive star exhausts its nuclear fuel, its core collapses under its own immense gravity. This collapse triggers a catastrophic explosion, one of the most energetic events in the universe. During a supernova, the star briefly outshines entire galaxies. The extreme conditions created in a supernova explosion provide the perfect environment for the creation of elements heavier than iron. These elements are forged in the intense heat and pressure of the explosion. In the heart of a supernova, atomic nuclei capture neutrons in a rapid sequence of nuclear reactions. This is known as the Rapid Neutron Capture Process, or R process. The R process is responsible for the creation of many of the heaviest elements in the periodic table, including gold, platinum, and uranium. These elements, so rare and precious on Earth, are born in the violent crucible of a supernova. The R process requires an incredibly high neutron density, a condition that is only found in the most extreme astrophysical environments. Supernovae provide this environment, making them the primary source of heavy elements in the universe. Neutron stars are the ultra-dense remnants of dead stars formed when massive stars collapse under their own gravity. They are composed almost entirely of neutrons, packed together with incredible density. When two neutron stars in a binary system spiral inward and collide, they create an even more violent event than a supernova, known as a kilonova. Kilonovae are among the most powerful explosions in the universe. Kilonovae create extreme conditions that are even more conducive to the R process than supernovae. The collision of neutron stars generates an abundance of free neutrons. These free neutrons are rapidly captured by atomic nuclei, leading to the creation of heavy elements. Kilonovae are now believed to be a significant source of the heaviest elements in the universe. In 2017, scientists detected gravitational waves and electromagnetic radiation from a kilonova event. This groundbreaking observation confirmed that neutron-star mergers are indeed a major source of heavy elements. The detection of strontium in the aftermath of the kilonova provided direct evidence of the R process in action. This discovery revolutionized our understanding of the origin of heavy elements. The newly synthesized elements created in supernovae and kilonovae are dispersed into the interstellar medium. This is the vast expanse of space between stars. These elements enrich the interstellar medium, providing the raw materials for future generations of stars and planets. The elements that make up our solar system, including the Earth and everything on it, were forged in the hearts of long-dead stars. The elements in our bodies, the calcium in our bones, the iron in our blood, and the carbon in our DNA, all originated from these cosmic events. We are quite literally made of stardust. The gold in our jewelry, the platinum in our catalytic converters, and the uranium in our nuclear reactors all have their origins in the violent deaths of stars. These elements are a testament to the power and creativity of the universe. We are connected to the history of the universe through the elements that make up our world and ourselves. The story of the heavy elements is a story of cosmic recycling, of death and rebirth, and of the enduring legacy of stars. The cosmic microwave background. Echo of the Big Bang. The cosmic microwave background, or CMB, is arguably the most compelling piece of evidence supporting the Big Bang theory. The Big Bang theory is the prevailing cosmological model for the universe's origin and subsequent evolution. Think of the CMB as a faint afterglow, a relic radiation permeating all of space. It's like a snapshot of the cosmos taken roughly 380,000 years after the Big Bang itself. In its earliest moments, the universe was an incredibly hot and dense plasma. This plasma was composed of ionized particles, a sea of protons, neutrons, and electrons, zipping around at tremendous speeds. During this period, photons, or light particles, were constantly interacting with these charged particles. Because of this constant interaction, photons were unable to travel freely through space. As the universe expanded, it also cooled. Eventually, the temperature dropped to a point where electrons and protons could combine to form neutral atoms. This process is known as recombination. Primarily, hydrogen and helium atoms were formed during this epoch. Following recombination, a crucial event called decoupling occurred. This is when photons finally separated from matter, and light could travel unimpeded through the universe. The CMB is essentially the light that was released at the moment of decoupling. As the universe continued to expand, something fascinating happened to this light. The expansion stretched the light's wavelength, causing it to increase. This increase in wavelength also meant a decrease in energy. These high-energy photons gradually shifted into the microwave region of the electromagnetic spectrum, hence the name cosmic microwave background. The CMB was serendipitously discovered in 1964 by Arno Penzias and Robert Wilson. At the time, they were working at Bell Telephone Laboratories. They were experimenting with a new radio antenna when they detected a persistent uniform background noise. Initially, they mistook this noise for some kind of instrumental error or local interference. However, after careful investigation, they realized they had stumbled upon something far more significant, a crucial confirmation of the Big Bang theory. The CMB's uniform temperature, approximately 2.7 Kelvin above absolute zero, was remarkably consistent with predictions made by the Big Bang model. Following the initial discovery, scientists launched a series of increasingly sophisticated satellite missions to study the CMB in greater detail. These missions included the Cosmic Background Explorer, or COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck satellite. These satellites map tiny temperature fluctuations, known as anisotropies, in the CMB. These anisotropies represent small temperature variations across the sky. These seemingly insignificant variations are incredibly important because they represent the seeds of all the structures we see in the universe today. These structures include galaxies, clusters of galaxies, and the vast cosmic web. These anisotropies represent slight density variations that existed in the early universe. These variations were imprinted in the CMB at the time of decoupling. Over vast stretches of time, these density variations grew under the influence of gravity. This gravitational amplification eventually led to the formation of all the cosmic structures we observe today. The CMB's properties are remarkably consistent with the predictions of the Big Bang model. This includes its temperature, its near-perfect blackbody spectrum, and the specific pattern of its anisotropies. The CMB provides a powerful window into the early universe. It allows us to study the conditions that existed shortly after the Big Bang with unprecedented precision. By studying the CMB, we can refine our understanding of the universe's evolution, from its earliest moments to the present day. The Enigmatic Dawn, Unveiling the Secrets of Population 3 Stars. The universe, as we observe it today, is a breathtaking panorama of galaxies, nebulae, and countless stars. Each celestial body tells a story, a chapter in the grand cosmic narrative. But before the familiar constellations and swirling galaxies, there existed a primordial era, shrouded in mystery. This epoch, long before the formation of complex structures, was illuminated by the very first stars, Population 3 stars. Their existence, though theorized, remains one of the most captivating enigmas in modern astrophysics. Join us as we embark on a journey to understand these elusive stellar pioneers. Population 3 stars are theorized to have formed from the pristine metal-free gas of the early universe. In the immediate aftermath of the Big Bang, the universe was composed almost entirely of hydrogen and helium. These were the raw materials from which the first stars would be forged. In addition to hydrogen and helium, trace amounts of lithium were also present. Crucially, Population 3 stars lacked heavier elements, often referred to by astronomers as metals. This absence of metals profoundly influenced their characteristics and evolution. The absence of metals in Population 3 stars had a dramatic impact on their formation and properties. Without metals to facilitate radiative cooling, the primordial gas clouds struggled to dissipate heat. This resulted in the formation of significantly larger stars than those we observe today. These first stars were also much hotter than their modern counterparts. Their immense size and high temperatures meant they radiated vast amounts of energy. Some estimates suggest they were hundreds or even thousands of times more massive than our Sun. Such colossal size meant that these stars consumed their fuel at an astonishing rate. Consequently, Population 3 stars had incredibly short, brilliant lifespans. Their existence was a fleeting moment in cosmic time, but their impact was profound. The formation of Population 3 stars presented a unique set of challenges. The absence of metals meant that the primordial gas clouds had difficulty cooling and collapsing. Metals act as catalysts, allowing gas to radiate away heat and fragment into smaller clumps. Without this efficient cooling mechanism, the gas clouds remained hotter and more diffuse. This made it difficult for gravity to overcome the outward pressure and initiate star formation. The result was the formation of fewer but much larger stars. These colossal stars represent a stark contrast to the smaller, more numerous stars that populate the universe today. Understanding the formation of population 3 stars is crucial for understanding the transition from the primordial universe to the cosmos we observe now. The immense size of population 3 stars dictated their rapid consumption of nuclear fuel. This led to incredibly short, albeit brilliant, lifespans. Their existence was a flash of light in the darkness of the early universe. These stellar behemoths met their end in spectacular supernova explosions. These supernovae were far more energetic than those we observe today. They scattered the first heavy elements into the surrounding gas. This enrichment of the surrounding gas with heavy elements was a pivotal moment in cosmic history. It paved the way for the formation of subsequent generations of stars. These later stars, known as population 2 and population 1 stars, incorporated these heavier elements into their composition. The search for population 3 stars is one of the most challenging endeavors in modern astronomy. Their extreme distance and short lifespans make direct observation incredibly difficult. They existed in the very early universe, billions of light years away. Astronomers must rely on indirect methods to detect their presence. These methods include searching for the chemical fingerprints of their supernovae. They also analyze the spectra of ancient galaxies for telltale signs of their existence. The task is akin to searching for a single candle flickering in the vast darkness of the cosmos. It requires the most advanced telescopes and sophisticated analytical techniques. Despite the challenges, the potential rewards are immense. The James Webb Space Telescope, or JWST, offers a glimmer of hope in the search for population 3 stars. Its unprecedented infrared capabilities allow it to peer deeper into the early universe than ever before. JWST is our most powerful tool in this quest. JWST is designed to detect the faint light signatures of the first stars. It can analyze the composition of the first galaxies, potentially revealing remnants of population 3 stars. This telescope represents a quantum leap in our ability to study the early universe. The data collected by JWST will be crucial in unraveling the mysteries of population 3 stars. It may finally provide definitive evidence of their existence and properties. This will revolutionize our understanding of the universe's earliest epochs. Understanding population 3 stars is crucial for unraveling the evolution of the universe. These first stars played a pivotal role in the reionization of the cosmos. This was a transformative event that shaped the universe as we know it. The radiation emitted by population 3 stars ionized the neutral hydrogen gas of the early universe. This cleared the way for light to travel freely across vast distances. Without this reionization, the universe would remain opaque and dark. Furthermore, population 3 stars seeded the universe with the heavy elements necessary for the formation of planets and life. These elements, forged in their cores and scattered by their supernovae, became the building blocks of future generations of stars and planetary systems. Without population 3 stars, the universe would be a very different place. Unraveling the secrets of population 3 stars is essential for understanding the dawn of the cosmos. It illuminates the origins of everything we see around us. This quest is a testament to humanity's insatiable curiosity. It reflects our relentless pursuit of knowledge about the universe and our place within it. The search for population 3 stars is not just a scientific endeavor. It is a philosophical journey into the heart of existence. As we continue to explore the depths of space and time, we move closer to answering the fundamental questions about our origins. The story of population 3 stars is a story of beginnings,
a story of creation, and a story that continues to unfold.